Hi, my name is Enrique Rico Ortega. I'm a research professor at the University of the Basque Country, and nowadays I'm working also at CERN, this big collider that is in the middle of Europe, that try to understand what is the nature at the most microscopic level. And the project I wanted to tell you today is related to try to understand this nature at this microscopic level, but in a different way, not with these colliders, but with the machines that, for example, is provided by IBM. This project is a collaborative effort, and let me see. Yeah. And there are several people that has worked in this direction. There are people from more quantum physics, from high energy physics, and also from condensed matter and tensor network calculations. For instance, the group of Wigner Institute in Hungary with Orle Getza, Miklos Werner, and Cornel Kaplas were leading the part of the tensor network calculation. Also, we have the collaboration from Madrid, from the Institute of Física Teórica, Alejandro Bermúdez and César Benito. Obviously, the support from IBM with Joana Frasenet and Pedro Rivero, and the part from the Basque countries, Jesus Cobos and Francesco Di Marco Antonio. So this collaborative effort is not only about the person, but it's also about the institutions. And happens that just recently, some weeks ago, it was installed a System 2, an IBM machine in the Basque country. And thanks to this agreement and to this collaboration between the Basque Quantum Initiative and the IBM, this project was also possible, and we have access to these machines to do this type of calculations. So what is what we have in mind and what we wanted to do? As I said, I'm working at CERN, and instead, every day is they take this proton and antiproton, and they accelerate it, and they make it running at a speed is close to the speed of light. And in this big collider of around a ring of 20 kilometers, is below the Lake of Geneva. And they make it scatter and collide, and to see what is the product inside of this proton and antiproton. These machines are highly precise and accurate machines to describe nature at the most microscopic level, and they are testing every day the laws of nature that we have. These laws of nature, at the most microscopic level, has been built since the 60s, 70s by the high energy physics community, and it's basically based on some symmetry arguments, and specifically in local symmetries, that is called gate symmetries. We will see in a second how this appears when we are doing this simulation with these quantum machines. And specifically the type of theory that is describing what is the structure and what is inside of our protons and of our nucleons, that we know they are composite particles, they are not the elementary particles, comes with this theory of QCD, quantum chromodynamics, or the theory of strong forces. The major player roles that are in these theories are elementary particles that are called quarks, that is the basic building blocks of our neutrons and protons, and the force that make it bind together and create the proton and the nucleon is called the glue. And due to the fact that it's a strong force, usually perturbative calculations they are not available. So the question that we have now is, instead of building these 20 kilometers rings experiments to do these precise and accurate experiments, can we do some type of simulation in some aspect in a tabletop experiment with IBM quantum machines such that reproduce this type of physics in some aspect? Obviously, we are not cover everything. Can we build a purpose-driven hardware to solve fundamental physics? Can we have a co-design? And this, I think, is an important issue about this co-design of hardware as a physics laboratory. And we will see two examples in the way. And that's why this sentence I wanted to put here, that history doesn't repeat itself, but it often rhymes, because we will see during this last century, this type of question has appeared, and several answers has been given in the way. So we need a machine that try to simulate this physics, this type of physics. So the first attempt, obviously, was with classical computers, and the answer or the way to build this type of machines was given around in the 70s by Kenneth Wilson, and the more precise machines that give you also accurate and precise measurements comparable with experiments were in the last decades. Again, here there is an example of this co-designing between computer scientists and physicists to try to have architectures that accommodate or that can simulate a QCD in classical computers. We know that this has limitations, and there are two aspects why this type of approach has limitations. First of all, is because the type of calculations is done with the Monte Carlo sampling, and for that we need probability distributions. As soon as a positive probability distribution, as soon as we don't have these things, there is what is called a sign problem, and Monte Carlo cannot assess this type of calculations. And the second, and is more, you want more philosophical, and this was given this problem was given or addressed by Feynman in the 80s, is that nature is not classical, and it's really difficult to simulate quantum physics with a classical machines because of the exponentially big Hilbert space. For these two main reasons, that we cannot not address calculation that has some problem, for instance, real-time dynamics, and because we expect that a classical computer cannot be efficient to simulate quantum mechanics, we need to go one step beyond. And this now is the notion of trying to use the quantum computers to do this nowadays a quantum co-designs for these strong forces for QCD. And this, in some toy model, this is what we have been trying to do, or we have been doing within this project. And specifically, we were looking at some dynamical properties of these theories, and how I was telling you that these protons of these neutrons is made of some elementary particles that were called quarks. And the quarks, they come together in the neutron and the proton, thanks to some forces, that is strong forces, and some glue. This glue is some energy that is attached in a string between the quark and the antiquark, and understanding the dynamics of these strings is something fundamental in these theories, and cannot approach obviously with type of Monte Carlo method or with more perturbative calculations. So here is the type of problem that we want to address: how to understand the dynamical process of this extended object that is a strings, that is some energy that is stored between this particle and the particle, and will be within these quantum computers. Why we want to see these things? Well, as I explained you in this collider, there can be a collision of this proton and antiproton. Because of the high speed, there will be a lot of energy that is released in these collisions, and then are created these new more elementary particles that is these quarks. We cannot see these quarks in the usual life because they are always attached together with this string that I was telling you of glue, of the strong force. If we have two static charges, if we have two of these static quarks, and we try to pull it apart to have two isolated quarks, the glue, the energy that we have to store in this string will be infinite, and we cannot split it far apart. And this is the notion of what is called confinement, and this is one of the big problems that have to understand this theory of QCD and the standard model, that is the whole structure of this particle physics. If instead of having these static charges just with glue, we have also dynamical charges, what can happen is that you store so much energy in the string that at the end the string breaks, and you start to create pairs of particle and antiparticles. These pairs of particle and antiparticles, they create what is called a meson. It's a type of new particles similar to the proton or the neutron that are called hadrons. So you break these strings. There is a process that's called hadronization, or the creation of these hadrons and mesons, and then you start to see the particles that appear in the usual life that we can see at the builds, for example, our atoms. So the question now with this is, how do this string of energy forms, how they wiggle and how they break and produce this hadronization? Can we use these quantum codecide systems to solve these dynamics? So we have to start with toy models, and we start with the hardware that we have at hand nowadays. And the answer, at least for some partial aspect, this is we answer in a positive way. So we take the chip of IBM, And what we realize is that has all the properties and all the structures, all the degrees of freedom that are needed to simulate this type of theories of QCD, of strong forces. Why is that? It's because we learned in the past about these Monte Carlo methods that the matter degrees of freedom, these quarks, can be described in a lattice in the degrees of freedom as situated on the vertices of our lattice. And this is something that we have in our heavy hex chip of IBM. And now what happened? The connection between matter degrees of freedom, I told you that they are always connected by this glue. So there will be what is called a gauge degree of freedom, a glue degree of freedom that is sitting on the links of this lattice. In our case, it's a hexagonal lattice. So we have the two main ingredients that we need as a degrees of freedom for the theory. We have the matter seated on the vertices. We have the glue, or the gauge degrees of freedom that are seated on the links of our lattice. Now we have to build the dynamics. Well, the first thing that we have to do to build the dynamics is give some energy to our matter degrees of freedom that are seated on the vertices. So this is simply a single gate acting only on the vertices of our lattice, and this we understand as the energy that costs to create an excitation on the matter. So it's the mass that we are giving to our particle in the system. The other energy is about how much energy is stored on the string that I was telling you about that is connecting the quark and the antiquark, about the glue. And this is measuring by a single qubit gate that is only acting on the links on this lattice. So we have already two elements, but now we need interactions. And the usual interaction is what is called the minimal coupling. And the minimal coupling corresponds to the hopping of the matter degrees of freedom mediated by the glue, mediated by this strong force. And this corresponds to a three-body interaction of this type. So now our matter degrees of freedom, our quarks, can hop in this lattice, but always creating some string, and then we will have, whenever this quark is going to hop, we are going to create a string in between this hopping term. So all in all, this is the simplest Hamiltonian, the simplest dynamics that you can formulate for a lattice gauge theory. And this is the one that we are going to introduce and we are going to simulate within the IBM machines. I was telling you that the whole theory of particle physics is based on symmetries, and specifically on local symmetries. This, for example, happened in quantum electrodynamics, but also happened in this toy model. In quantum electrodynamics, we have the Gauss law, and we know that the charge is the source of the electric field. So something similar, and this is what is called Gauss law, and this is something similar that happened now in this system. We have, and this will be important for error correction and error mitigation. You will see in a second, and that's why I wanted to take some time in here. This dynamic that we have in here, they commute. They have a symmetry that is a local symmetry around the degrees of freedom that happen on the vertices. This is because these degrees of freedom that we have in here are just qubits, and because of the type of interaction that we have in here, the type of system that we have is a set2 gates theory. It's just a theory of qubits. What happens that now the symmetry that we have locally, our gates symmetry, is something about the parity. It's the parity if all these degrees of freedom happen around the vertex. And to be in a physical subspace, the parity has to be positive. Everybody has to fulfill this property. If under the evolution this is not fulfilled, we are outside of the physical subspace, there will be a red flag, and then we understand that we have a failure in the evolution, and this will help us to have this error mitigation. These are the type of new techniques that we have introduced in the whole plethora of tools that we have about error mitigation from IBM. Okay, so now we have already identified the degrees of freedom. We have identified the dynamics. We have identified the symmetry that will help us to also do the error mitigation techniques. What are we going to do next? We're going to put all of these aspects in the machine, and we're going to run the machine. We know that the machines are not error-free. We are not in a fault-tolerant era. So we need to understand how to handle with the errors. And for that, instead, we are going to do a total decomposition of this interaction that I was telling you, this single qubit rotation and this 3-qubit interaction. So instead of starting with the whole dynamics, we're going to start only with the interaction. So we are going to put the mass and this string strength equal to 0, because in this case, we have already an interacting system, but we have no trotter error. There is only our whole Hamiltonian is just based on this single block for the whole lattice, obviously. But all the errors that we are going to see with this Hamiltonian are just hardware errors. Can we handle hardware errors without introducing the trotter errors? If we can do this step, then we can go to most general scenarios in the phase diagram. So this is now what we do in here. We are just dealing, as I said, we don't have this on-site interaction. We have just the interaction of three-body coupling. And the raw data is obviously a noisy data. It's good that now that we have a whole toolbox of different error mitigation techniques. One, they are more usual in the whole IBM platform, like Pauli twirling or this observable depolarizing renormalization. But I wanted to stress, and I wanted to tell you today or describe two specific ways of doing this error mitigation due to the amount of symmetries that has this system. And this helps us to also to introduce these new error techniques. This, we call it gauge dynamical decoupling and gauge sector correction. So as I was telling you, we have this local symmetry. It's a symmetry that happens around the vertices. There is a property that has to be fulfilled. And if this property is fulfilled, then we are in a physical subspace. Okay? If this is not the case, then we are in a physical subspace. So this is just being this positive or negative. This is how we identify this being in a physical or in a physical subspace. Now what we can do, if we jump, if there is some amplitude that is going to the unphysical subspace, what we can introduce is a random configuration in this, because we know where is going to be sitting the unphysical the error, because it's just measuring where is this Gauss law that has been failed. We can introduce now some random phases, both in the space where is has been created the error, and in time. This is a fluctuating phase that is going to fluctuate also in time. And why we do this is because now we have a highly fluctuating configurations in the unphysical subspace and something that remains stable in the physical subspace. Under now any expectation value, the unphysical subspace will average to 0, and all the contributions will come only from the physical subspace. The second type of error technique that we wanted to mention is about gauge sector correction, again, based on this symmetry that we have around the vertices. When we computed the configuration that happens in the matters and the gauge degrees of freedom, we can check if this condition is fulfilled. If this condition is not fulfilled, there will be a set of errors in the whole lattice. And we discard whenever there is the number of errors, the density of errors is really high. So we only remains with a configuration with the number of errors that happens in these measurements are low. Why that? Because if they are low, with high probability, we can understand where the error came from. We can correct the error, and then we come back to the physical subspace. So with these two techniques based on this local symmetry, we managed to recover the exact data that also coming from the tensor networks of classical simulations. In all the plots that I'm plotting here, the dots correspond to the experimental data. The shadows correspond to the errors that we estimated from the experiment, and the lines correspond to the calculation from tensor network calculation, classical tensor network calculations. Okay, now we know that we can dominate also the hardware error. Let's see a possible configuration that we built. As I told you, we are interested in creating a particle antiparticle and create a string of this glue, of this energy that is connecting this particle antiparticle, and see what is the dynamics that happening here. Again, here I'm stay with Hamiltonian. That is only about the interaction term. There is no local term, but this I'm going to show you now can be generalized to any possible mass or energy of the string in the phase diagram. The number of qubits that we managed to do, the maximum number is almost the whole chip. This 144 number of qubits, depth almost of 200 qubit depth. what means to have a total number of 2 qubits gates in these simulations of around a bit less of 8,000 2-qubit gates. One of the nice things also about the statistics and also for error correction is that this platform allows us to have huge statistics, and this is something that we are using obviously a lot for the error mitigation. So this is the type of now of what's going on in this system. We can carry on with we can understand what's going on with the configuration and the occupation of all of these qubits that are in our chip, identifying again the vertices as a matter degrees of freedom and the links with these glue degrees of freedom. And we see that at this particular value of the mass and the energy of the string, there is some collapse or revival of this string that is spreading the energy or concentrated back to the string. Can we go to more general scenarios in the phase diagram? Can we go to a part in the phase diagram that can be some interesting to understand this confinement that I was telling you, how it's creating this proton with these quarks, anti-quarks, and glue. In fact, this is the case. Although this is a toy model, there has a lot of structure, the phase diagram. There are some parts that are what is called a deconfined phase. There is a part that is called the Higgs. The Higgs is exactly what I was showing to you. And the important part, more about this understanding of confinement, corresponds to this part in the phase diagram. So we can follow again what's going on in the Higgs I was showing you, or in the confined phase. But the important point in here I wanted to show you is about the confined phase here of the system. What does it mean to have a confined phase? Is that this long structure that we have, this string, is something that is stable. This is the first point. And this is something that we see in the simulation. It's not that it's spreading and collapse and revival that was happening in this Higgs or in the deconfined that we have here the results. But we have a stable structure that is our string. And now we want to identify modes of this string that happens in the system. And there are, just as having a strings, there are two modes of strings that you can, they're quite logical. First is about a longitudinal move. This is what is correspond to this yo-yo mode. This is a first order movement and correspond to this oscillation that happening here, this fast oscillation, correspond to this yo-yo mode. This is a longitudinal movement. The second, in the lattice, is a second order process, it's a bending process, and it's how the string is trying to bend around and to rotate. And this, although it's not complete, but this corresponds to this enveloping here. This is a long frequency that corresponds to this bending modes. So it is nice that we can see how the string is moving in an IBM machine and see that this is stable, and we recover this yo-yo and this bending mode. Just to finish, then you can go crazy, and then you can realize new configurations and to see how these strings break and recombine. And we start, for instance, with this three-string configuration, where again we have the glue that is sitting on the links of the lattice, and we have the quarks sitting on the vertices of our lattice, and with the type of interaction that with this mass and this energy of the string, we let it evolve, and again we can see that we follow the tensor network calculation, and also with our machine, and also within the error bounds, and even with the quantities that has a small amplitude, like this quantity that we have here in these configurations. So all in all, I hope well, I managed to show you that this was one of the examples, because nowadays my colleague will talk also about some similar works, where now we are trying to do a really strong effort to try to apply these quantum simulations to high energy. And I think it will be important about all these concepts of co-design and collaboration between different institutions and different computer science or physics, to try to have a hardware that accommodate the physics that we want to see, and also obviously, because we are not still in the fault-tolerant era, is how to handle the errors in these machines. As I told you, this has been already explored with classical machines with this blue jeans type of approach, but now obviously we have to go one step beyond, and our machines are not anymore classical, but we have quantum machines, and this is the dream, if you want, of Feynman, to try to simulate quantum physics with a quantum machine. We are still far away for the whole QCD adventure. We need to obviously to scale it to larger lattices, less noisy, 3+1 dimension, not abelian statistics, and this is what is needed for the full QCD. But we are in the way, and we know what is the path, and we are trying to build all these steps. So let me finish once again with my collaborators, and thanks to everybody. And now I give the floor to Nikita.